Morning, everybody. I'm Bob Laughlin from Stanford Physics. I have a very strange mission this morning. I'm keynoting for a bunch of people I don't know in a field I'm rather alien to. And so I had to guess what would be good material for you. And God help me, I hope I guessed properly. And if I didn't, well, such is life. Okay? Now, so I'm going to talk about principles and try to connect that with the theme of your conference, which is complexity and how you parse complexity. This, of course, is a Rube Goldberg cartoon showing something that's complex. And the reason I picked this as a starting image is because it's silly. What's silly about it is the complex thing won't work. Okay? And so there is a link that I want to try to make this morning between simplicity and things that work. And I want to make that link both forward and backward. That is to say, there is a theme that we're trying to do to connect what we see in the physical world with life. And the distillation of what I want to talk about today is that there's a machine involved which has to work. And life is busily struggling, trying to make its machinery work. And sometimes when that happens, simplicity is born as a means to an end. Now, So let me start off with something simple, right? This is a conference about complexity. What is complexity? This is with all fairness to Justice Stewart, I can't define it, but I know it when I see it. Complexity isn't pornography, but it's close. Now, there's also this existential thing that everybody sort of yearns for simplicity, not knowing why. And there's some art involved in vanquishing complexity, art that's difficult to achieve. We saw a quote from musicians about this principle, so we kind of all know it. So there's an anthropic part of this concept of simplicity having to do with how we see the world. But maybe it's all imaginary. Maybe the world's just complicated, and we're imagining something that isn't there. So now the conversation about complexity, simplicity, back to complexity, of course, always begins with the weather. And back in the 50s and 60s, it was figured out that the equations of hydrodynamics are unstable. And so this is the beginning of what we call the original round of complexity, dealing with how complexity comes about. You start off with something simple, and then complexity comes about. The simplicity is this, so-called closed Navier-Stokes equations. As far as we know, they describe the weather, well, with some water equation state, and they describe the weather. But we also know that they are unstable depending on the Reynolds number. And there is one limit where the equations are stable, and there's another when they begin to do crazy time-dependent things. Now, this is the genesis of the link between complexity, concept, and pattern formation. So we talk about looking for patterns. I'm trying to understand what is happening. I look for patterns. For example, here I see this wigwag of the fluids. And so I'm trying to understand what I'm seeing by seeing these self-generated patterns. Now, an idea that I want to throw out to you this morning is that right? Okay? Is that right, or is that a deception that has been created by your mind because of how your mind works? Underneath the Navier-Stokes equations is something very chaotic. And we sort of know that we're blessed that nature organizes itself so as to create the equations of hydrodynamics, which are a very simple thing. If the fluid isn't dense enough and other things, collisions aren't rapid enough, the equations of hydrodynamics do not emerge, and at that point you lose all ability to make predictions. So in this case of hydrodynamics, your ability to predict or to not predict, which is to say to understand or not understand, rests on something nature did. Nature organized itself and created a very simple thing, which we describe by equations. Why? Because the simple thing is redundancy among measured quantities. We say there are only a few important quantities. Well, it means there's lots of quantities there, but they're related. And those relationships are rendered in equations. So when this kind of thing happens, nature creates the equations. And it does so by principles of organization that are still to this day rather poorly understood. Now, but we know it's true because we have predictive power with hydrodynamics. Now, so here's message number one. Law, in the sense of our understanding it, is a complicated concept. But in physical science, many times, law is created by a microscopic self-organization process. And in those cases where this process is occurring, there isn't any law. For example, if the number of particles is too small, you don't have thermodynamics. You have, and all the amazing predictive power you have for thermodynamics goes away because the self-organization hasn't happened yet. So we live in the physical sciences in a place where the organization and the laws that it makes come from heaven. And that's an idea that's built in to the way we do physical science. Now, let me change the subject. What about biology? Okay. So we have this urge to think about biology the same way. We see regularity and simplicity, and we make a connection. Oh, this is like what we see in the natural world. What's happening according to this point of view, and it's written in Darcy Thompson, is nature found a way to exploit those laws. And so what you're seeing is implementations of physical things. In other words, the idea is that biology is built on physics. And biology is using the laws of physics to make organisms. There are, what the hell? There we go, yeah. There are tons of parallels that one can draw. Actually, I just photocopied this picture out of Darcy Thompson. This is a little hand drawing of Doc Edgerton's famous milk drop splash. And this is a hand drawing of a hydropolyp. So the idea throughout this book is that nature is doing the things it does because physics tells it to. Okay? Now, the idea that I'm trying to throw out this morning is that that's wrong. That's not only wrong, it's really wrong, as in conceptually wrong. It is not, I'm going to propose that it is not the case that nature looks like physics, biology looks like physics sometimes because it's exploiting physics. It's instead that it reinvented it. In other words, there is something going on in biology that has nothing whatsoever to do with physics. It has more to do with computer science. It's making things. How do you make things? And the impetus in a living thing is to make something that works. In order to make something works, it has to be stable to perturbations. That is to say, it has to have some universalities going on it. Otherwise, if you kick it, it'll get knocked off kilter and won't work anymore. Now, I'd like to illustrate this idea with a specific piece of work that I did a number of years ago about what I call the length problem. So here I have a picture of a skeleton of a fish, and you'll see it's very complicated. Has a lot of detail. This you already know if you've eaten fish, but also you know that all the fish are the same. Right? You take apart a fish of a particular species, it always looks like this. So this intricate engineering that's done here is built in to the map of how the animal is made. And all of those things in there require the measurement of length, either absolutely or relatively. But there are a whole bunch of lengths. If you were to write a computer program to draw this picture, it would probably need several thousand lengths in it. Now, there is a worldview that you find in life sciences sometimes, because it's so complicated, that evolution just did this. Okay? Evolution just figured out a way to do this. But is that true? It's very dangerous when you invoke magic to explain something that's very regular. Okay? It makes rather more sense that nature figured out how to measure the lengths. Okay? And it's doing this on a massive scale, including all the way up to whales. And it made a discovery about how to do this, which we don't understand yet. Now, when we begin looking at the underpinnings, we find the whole subject of morphogen gradients. This is an old idea, and it's actually backed up by labeling measurements in embryology. Now, I don't want to get into details of what I'm showing you here. These are actually antibody labelings rather than GFP. But the point is that there's expression maps that are going on here, and there are diffusive things happening that map out part of the original body. This is known in the business as the French flag model. The idea is you have some source of something here, like perfume, and then it diffuses away. And as it diffuses away, its amount of it gets less. And then you have machinery that detects how much it is, what the density of this perfume is. And when it gets down to a certain level, it throws a switch. And that's how you make structures. The length scale here is determined by interplay between the diffusion constant and the rate of destruction of the substance, whatever it is. So it's the length. The length is coming from the phenomenon of diffusion. Now, the problem begins when we start thinking of complicated things. Here's a fruit fly. How in God's name can a French flag make a fruit fly? Well, you say, well, it's evolution. Evolution can do anything. No, it can't. No, it can't. We know if you're doing engineering, there's a tip-off that you haven't understood what's going on if you cannot write equations for it. Why? Because it's stably true. Okay? You know for sure that there's something going on that's stable to perturbations. And when that happens, you've got equations that are describing what's happening. So there's a piece of this puzzle missing. Now, oh, come on. Come on. This is the wrong picture. These people aren't supposed to see this yet. Okay, yeah, there we go. Yeah. So if I were a actual engineer and I was trying to map out lengths, the way I would do it is I would take the diffusion thing that we just described and I'd make it dynamic. Okay? I'd make it time dependent. In fact, what I'd really like to do is make something like compressional sound. If I had compressional sound, then I could do it because once I've got a stable speed scale, then I can measure out lengths by means of time. So chemical reactions are very good at measuring time. They're very lousy at measuring lengths. So the technical way to do this is to kind of create something that propagates with a fixed speed. Now, diffusion will kind of do that. In fact, there's a case that you know of. This is a particularly fast reaction diffusion that has electrical stuff behind it. But there are other kinds that aren't electrical, and your body's full of them. And it's true that all right. Yeah. And you can make waves. You can make waves with diffusion by means of having competing generation and killing chemical reactions. This is the famous reaction diffusion idea of Alan Turing. Unfortunately, the literature on this subject is incredibly confused because the literature, if you Google for it, you'll see on Wikipedia that reaction diffusion is a way to make patterns. And in fact, this is a particularly simple set of reaction diffusion equations called the Gray-Scott model, which has this complex phase diagram. The two parameters k and f are in here. And depending on what k and f are, you'll get all sorts of behaviors. Okay? You take this model and adjust these parameters and then let it go, and a whole bunch of stuff happens. Like, for example, this is one of the things that can happen. It can make these little stripy things. This is a particularly neat one. It's like boiling water. Okay? Constantly boiling water. Here's another one. Little snakes. Little wormy snakes that kind of intertwine with each other and grow and do that snaky thing. And then here's one, that little solitons. And there's one I didn't show here that has these solitons stable and some other little pink ones coming in and out periodically. So this set of equations is known to be unstable. So we have the idea of pattern formation as looking something like life. On the other hand, real biologists just dismiss it because they're unstable. It's a toy. Okay? Now, holding this thought, I want to show you an experiment. Oops. Oh, this is one more thing it can do. It can make little beehive cells, depending on. Right. Now, I'm going to show you an experiment. This is done in vitro with a handful of proteins, I think 4. And they're just put in a petri dish with a bunch of ATP and some salts. And so they start doing these time-dependent things. And there you can see there's this little wave. The times up here are in seconds. What the colors are don't matter. It's labeling of proteins by various means. And what you see is they're moving around and dancing on the scale of minutes. Now, the reference, by the way, is covered up down here. This is a PNAS paper from 2010. Now, what's special about this experiment is that the proteins in question are very notorious proteins. They're called the Min proteins in E. coli. And they were originally discovered at Harvard through a mutant, the Min mutant, which wouldn't divide properly. And so people understood that these proteins had something to do with the machinery by which a cell divided. So in 1999, one of that group named Pete DeBoer labeled the proteins in actual coli and found what they did. This is a follow-on experiment that was done just to make sure that these proteins and only these proteins were involved, even though the theory was pretty clear at that time that that's all it was, just these 4 proteins. Now, but what happens in coli is not this. What happens in coli is this. The proteins in question flock from one end of the bacterium to the other like birds, and they go back and forth in a wave-like motion with a round-trip period of about 40 seconds. They do lots of other things that are sort of reminiscent of trapped waves. For example, if you knock out the gene that actually does the division, you see the thing gets too long, and then it begins to make these sort of waves that are doing that. Okay? And here is one where it's made standing waves. So what's going on here is looking like sound waves that are trapped in a box. Now, this is, of course, an enormous subject and a little bit disreputable now because the physicists are very interested in this and the biologists think it's a sideline and they won't get any money to study anymore. However, I remember the day I saw this. Even I, a mere physicist, know that that is standing waves in a bottle, like blowing across a Coke bottle. Okay? Even I know that. And the fact that these proteins were discovered as division proteins is telling you that this darn thing is using a resonance, a time-dependent resonance inside itself to find the midpoint. It's probably actually doing a lot more because the DNA has to be swept into the two halves, and who knows how that works. But what you do know is that when you knock out this motion, the bacterium won't divide properly. So here is what I myself think is the smoking gun hydrogen atom experiment of morphogenesis. In other words, there was a reason to suspect that there was something going on with time in living things. Why? Because you can't engineer enormous bodies with plasticity unless you have a meter stick that can be changed. Okay? And how do you do that? All you have to do is invent one thing, which is a way to get the speed scale constant, and then you do the rest with time. And it's perfectly reasonable to speculate that the reason nobody found this before, firstly, is because these experiments are darn hard. You have to label the proteins and label the right ones. Secondly, all of the powerful spectroscopies of biology are slow. So it's just the way they work. They're not set up to see time. Time is really hard. So there could easily be a whole bunch of dynamic stuff going on inside your body that modern techniques don't see. Now, so the data are telling you that the living thing found a way to take this unwieldy reaction diffusion dragon and tame it, make it behave for a purpose, namely to measure its length out. And therein lies the nut of the matter, that a living thing is not looking for patterns, and it's not looking to be entertained, it's looking to live. And in order to live, it needs engines and machines that it can control, because if the machine will do something different depending on the circumstances, then your machine will fail, and you can't win the construction and function battle with your enemies. So now, a brief digression and I'll quit. How could it possibly do this? This complicated, unstable chemical reaction. How could it possibly do this? Well, it turns out there's a trick, okay? And it's a physics trick. So it's very hard to justify it empirically working backward from the chemistry, especially that nutty, that crazy patch thing that I showed you. There's an idea, and that is that reaction diffusion equations can be made powerfully linear by the simple trick of turning up the amplifiers in them until you're just on the verge of oscillation. Okay? They're critical. So there's a criticality trick that'll make it work. And not only that, but this criticality trick is known to be operating in your cochlea. It's a thing called the cochlear amplifier. So here I've written the basic idea that you've got a harmonic oscillator, this little hair, that's incredibly damped. So what you do is you put an amplifier at the bottom, and you put forward feedback and make anti-damping. And you turn up this amplifier gain, okay, until it just cancels that. If you turn it up too much, the thing will oscillate. So the way you find the right point is you turn it up until it begins to oscillate, and then you back it down a little bit. And this is the reason that when you take a microphone up to your ear and measure, you'll see sound coming out of your ear. It's all those amplifiers tuning and detuning through their instability point. Anyway, there's a big literature on this called the cochlear amplifier that you can read. Now, in the 2 last seconds, there's an electrical analogy. Then I'll flash before you. The way amplifiers work in simplest reaction diffusion, which is to say your neurons, is by a 2-terminal amplifier, better known as a laser gain medium, or a tunnel diode, same thing. And the physics of those 2-terminal amplifiers is that you can't make them amplify without also switching the sign of their reactive part. physically impossible to do this, because if you do, it won't be stable. It's the principal causality. So this is a picture not of biology, but of actually laser gain media. And what you see is when it becomes amplifying, the real part switches sign. Well, that same principle applies to resistors. Any resistor that's negative, that has negative resistance, also must have negative capacitance in order to be causal. And so you put all that into the equations, and it works. So you tune the amplifier so it exactly cancels this real part, and the crazy dispersion relation for the waves becomes exceedingly linear. Here, look at the red line. This is frequency versus momentum, and the imaginary part has been crushed to zero. So what you've effectively done by this trick is you've taken this unwieldy reaction diffusion equation and you've turned it into the moral equivalent of compressional sound. It acts just the same way physically as compressional sound, but it isn't compressional sound. It's something emulated by engines. Now, these are the equations of those of you who are reaction diffusion aficionados. Now, let me come back to the core question. We're talking about complexity. I, as a physicist, like to turn it around. What is simplicity? It isn't a perception. What you're perceiving is actually true. It's that what you're seeing and measuring becomes exceedingly redundant because of some emergent thing that happened. And in the physical world, we call that law. When there's a quantitative relationship among measured things, we call it a law, especially if we can render it in terms of equations. So when we see simplicity, that's what it is. And usually, it means that underneath is some law operating, because the universe likes to be chaotic. And it is, in my experience, pretty chaotic unless something prevents that from occurring. And now we have a fundamental difference between physics and biology that I have thrown out for you. In the world of physics, these laws just are. Okay? The laws of statistical mechanics just are. Obviously, the laws of regular mechanics just are too. But we live in a world where the diktat comes down from heaven. In biology, I submit, this is wrong. The regularities that you see in biology don't come down from heaven. They are made. They are made by the biological system for the purpose of engineering itself. And the ones that I know about are made by leveraging a principle of engineering, such as the criticality one that I mentioned to you before. The living thing is trying to beat its competitors. It searches around at random in the dark, discovers, quite by accident, an engineering principle that allows it to make things that its competitors couldn't make, and suddenly its competitors are toast. In this particular case, I am suspicious that this dynamic invention that I described to you is in fact very general. It's in all of us. And that is the precursor of both neural action potentials and what's happening in the cochlea. Now, those are speculations, but I'm a theorist. I'm allowed to make speculations. I think, but for this conference, let's leave the speculations aside and say that the issue on the table now is universality that just is versus universality that living things create. Okay, everybody, that's it. Thank you.
So, if I understood everything correctly, but what I think you're saying is that biology requires competition, but the competition is determined by the physical laws that come down from heaven.
Not quite.
Not quite.
No. I'm trying to throw out actually a much more radical idea that the physics connection with biology is rather remote. That it isn't the patterns that you see in biology that are all through Thompson's treatise are not the laws of physics rearing their head. They're instead symptomatic of some new rules that the living thing created. And their similarity to the physical laws we know are just because they work. Okay, it's things that work. So I think I'm proposing that looking for the secret of life in complexity of physical things is not only wrong, it's absolutely backwards wrong. Life doesn't like chaos. Life is engineering. Life is in a battle all the time to invent things that vanquish the complexity that it lives in. And it is able to do that because sometimes it finds a way to do it. And then there are little mouse droppings. You see symptoms of its having successfully done that in that the things you measure become redundant. But it's not physics working. It's actually economics. Namely, the thing basically finding a way to make things stable so it can get rules of design and building and construction that work.
Hi, I'm John Pepper. I'm an evolutionary biologist studying the evolutionary underpinnings of cancer. And I wanted to throw out an amusing note on terminology. So often our terminology divides us in our interdisciplinary efforts. So I thought it was illuminating to point out that this is a case where the terminology can unite us. Evolutionary biologists are fascinated by these recurrent solutions that arise with such regularity that they become almost universal. Not just one fish species, but every fish species. Often every type of organism that confronts the same kind of problem will end up with the same kind of solution. And so evolutionary biologists talk about this a lot, and they call it convergent evolution, or just for short, often just convergence. And there's a great deal of convergence that creates all the good things in biology, and also is why cancer always converges on being something very nasty and unfortunate. So convergence is extremely important within biology, as well as in ways it converges outside biology.
Exactly. So for me, I'm interested in weighing the question of whether there's a principle that gets discovered many different times, or it was discovered once in the ancient past and then replicated itself.
That's another another favorite question of evolutionary biology.
And it's very hard to answer that objectively. I'm an Occam's razor person. If I find something really, really sophisticated, I'm inclined to guess that it was invented once.
We have a special apparatus in evolutionary biology called the method of independent contrast, where we can ask, did this arise once and just stuck around, or did it arise many times?
Right.
We have specific techniques for answering.
The point is, I guess, the potential for something very similar to arise a second time isn't magic. It comes from a discovery of something that is engineering.
Yes.
Okay.
Yes. Either repeated or conserved.
Correct.
Discovery.